Hess's law is a rather simple way to find the enthalpy of an unknown reaction without having to do an experiment if you know the enthalpy of a couple of related reactions. And it's a little bit of puzzle. The idea is pretty simple. I have these known ones that are related, and if I add these up, I can get my new one. Now we rarely can just add them up as is. We usually have to manipulate them a little bit to get them to add up to the final one. So let's begin. We start to make some observations. How are these related? You try to find something in your final equation that is only in some of your initial equations one time, because it has to be at the same coefficient and on the same side of the reaction. So here we have 4 NH3s, and up here the only time we see NH3 is over here in the second reaction on the left, and we happen to have 2 of them. Well, we need 2 more of those. So what we need to do is we need to double this whole reaction, okay, times 2. So I'm going to get 4 NH3s, 6 NO2s, 8 N2s, and 6 water liquids. Double all of that. And if we double that, we also have to double the enthalpy, so negative 2024. Okay. Now the other thing we can do, if we took care of the ammonia, we can look at the oxygen, and the oxygen only appears one place as well, so it's in the first one. Since the ammonia only appears in one spot, we know that this second one is right. The oxygen is only in the top one, so we can use the oxygen to do that. The nitrogen would be a bad idea since it's in both reactions. That's going to be an intermediate of sorts. We're going to see if that cancels out. The water, we could use the water as well, but that one's already taken care of in the same reaction as the ammonia. And then there's other things up here like the N2Os that we hope will cancel out when we're all done. But we can do this entire reaction just by looking. The ammonia told us the second reaction. We needed to double it. And the oxygen is going to tell us the first one. So I need 3 oxygen molecules, and I need them to be reactants. So I'm going to triple this whole reaction, but I need to reverse it as well to get the oxygens on the other side. So 3 oxygens plus 6 N2s make 6 N2Os. Okay, and we just reversed and tripled that whole thing. So we can reverse our delta H as well. Now it's going to be positive instead of negative because we changed the directions, and it's going to be 492 because we need to triple it. All right, and let's see, double check to make sure that cancels out. 6 N2Os on that one, 6 N2Os there, those are good. And 6 N2s, and then this is going to reduce down to 2 N2s. And if we tally everything up, I have 4 NH3s plus 3 oxygens left over on my reactant side of all of these, 2 N2s, and 6 H2Os. So by tripling this reaction, changing the sign and tripling, and then just by doubling this one, we were able to get our enthalpy. So now we just add those up. We get negative 1,532 kilojoules. Okay, this one's a little bit bigger, so it's going to be a little bit more of a puzzle. But the goal is the same. Find something in the bottom that tells you how to conduct yourselves with these 4 knowns. So we'll just kind of go one by one and see where that takes us. The first thing is 2 borons, 2B. And the only place that occurs up in these 4 reactions is down here in the 4th one, another 2B. That actually tells us it's in the right spot with the correct coefficient, so we're going to leave that bottom one alone. Okay, now that does a couple of things for us. It tells us the boron is good, And even though hydrogen and B2H6 are not down here, it tells me that they need to be in those positions as well. You'll see why that's going to be important later on. Because here's the oxygen, the second term we get to. Oxygen is actually going to be really hard to do. We can't balance this right now because oxygen appears here and up at the top. So we can't balance that one right away. We're going to have to come back to it. Now the B2O3, I need 1 mole of that as a product. That means I need to reverse my first reaction, and that's going to give me B2H6 plus 3 O2s makes B2O3. Now I have that B2O3 as a product plus 3 H2O, and I need to be careful here. Those are gases because there's liquid ones down there as well. So we just did that, reversed that equation, and if we're going to reverse it, we're just going to change the sign. So now I'm at negative 2035, and this first one is taken care of. Okay? Now, these next two are a little harder because I can't really balance anything down in my bottom equation from those. But since I know, if I look at our first one with its 2 borons, since I know I need these 3 hydrogens to cancel out, I can use that information over here to move this hydrogen to the opposite side. I have 3 hydrogens here as a reactant. I need 3 hydrogens over here as a product because I know this hydrogen is good. So if we reverse the second one, or this third equation down here, and triple it, all right, so we're going to reverse it and triple it, then we can see how our hydrogens will cancel out. So that's going to give me 3H2O liquid turning into 3 H2s, and now I've got 3 halves an oxygen, which is fine. Gas. Okay. So now we're good with that one. And our new enthalpy for that is going to be, we reverse it times negative 3. Okay, we reverse it and times 3. That's going to give us positive 858 kilojoules. So now that one's good. So our last one is just how do we cancel out the waters. We can kind of take a quick inventory here and see that everything else is good. I've got my 3 hydrogens, those are good. My 3 halves an oxygen down here, and 3 oxygens up there. Well, 3 halves, that's 1.5. So if I cancel that one out, we can do it with fractions, not a problem. Those 3 halves an oxygen are good. This will be now 3 halves an oxygen, which happens to match what we have in our final equation. So that just kind of took care of itself. That was a nice feature. We know our B2H6 is canceled out. I've got 1 there, and I've got 1 over there. And the only thing we haven't taken care of is the water, which is what this last reaction is going to do for us. We have 3 gaseous waters on the right that we need to cancel out over here, and 3 liquid waters on the left that we need to cancel out. And since these are going to be the same coefficients, we can do that for both of them. Now, for some odd reason, they already have coefficients of 2. We need them to be coefficients of 3. And we actually need to flip it so that the gases and the liquids are on opposite sides so that these will cancel out. So flip it, and then if we multiply it by by 3 halves, we can get coefficients of 3. So yes, fractions can be a part of this thing. That will give me 3 H2O gases turning into 3 H2O liquids. All right, so what we did there is multiplied it, we reversed it, and we multiplied it by 3 halves, and that's going to give me an enthalpy of negative 132 kilojoules. And now that one is taken care of. Okay, so we reversed it and multiplied it by 3 halves to get coefficients of 3. Now that's going to let my 3 gaseous waters cancel out, and my 3 liquid waters to cancel out as well. That's a big mess of a puzzle, but everything that we're left with 2 borons, which is there, 3 halves in oxygen, which is there. Everything else cancels, and 1 B2O3, which is there. So we're left with our balanced equation after all of that crazy work. The only thing left to do is to add up all of our enthalpies. Okay, so we have all these guys here. Now we changed the sign on this first one. We 3 halves that one. We multiplied that one by 3 and changed the sign, and then we left the last one alone. We add all those guys up, and we get this final one will be 1273 kilojoules. So the benefit of that is now we have a predicted value. We don't actually have to run this in an experiment in a lab. We can use known equations to get a predicted value mathematically of how much energy a reaction should absorb or release.